So first of all, I need to finish up something from the last lecture that I didn't get around to. But it's a good place to start the current lecture because it will remind us of some concepts. So I want to show you how to prove very briefly the following important fact, that whenever I have a category of diagrams like this, or also called presheaves on some small category, that this is an example of a Cartesian closed category. And these are, in some sense, certain very simple and useful Cartesian closed categories because you have a kind of intuitive idea of what they are. They're some kind of variable sets. Right? They're sets that vary in a parameter coming from the index category. So it was a homework problem to show that these things have products. So if I take two such variable sets or diagrams, that I can make the product, and I think I told you how to do it. I said for every object X in the category C, let the product simply be the product of the values of these two functors. So we're going to make the products pointwise. This is pointwise. And then whenever X goes to Y, well, this is contravariant, so whenever X comes from Y, like that, we need to find a way for this thing to go to this one. And how should we do it? Well, the value over here we've already decided is going to be this. But now we have to get from here to here. Well, that's not hard because associated to A itself, we're already assuming is an action on this arrow, right? So there's some thing right here, right? Let's call this map here H. Well, then A acts on H here, and A also acts on, or B also acts on H, and now we know that the product is a functor, so producting up those two maps gives us the map that we're looking for here from AY to BY. Yes? So that was the homework problem. I don't know if anybody did it, but it's very straightforward to show that you can make products like this pointwise. And in fact, you can also make coproducts pointwise too. So I don't have a thing here. So here, same for A plus B. You can make those things pointwise too. But what about the exponentials? That's the interesting thing. So exponentials. What are we going to do about B to the A at X? Well, the first thing you might think of trying is just to make that pointwise too. That certainly is the first thing to at least try and see if it works, right? So let's take that set where the values here are in sets. So for two sets, you can always make the function set, the set of all functions from one to another, right? And now here's, again, Y coming to X. Well, let's see here. We have B, we have A. Where's the? So we need to get to B to the A at Y, which we're wondering maybe could be defined like this. So we need to get a map. Sorry. We need to get a map like this, right? That's what we need. So we've got B X to BY by assumption. We've got AX to AY by assumption. But of course, there's a problem here because this is in a covariant position and this is in a contravariant position, right? So from these two maps, what can we put together? Well, we get BX AX, and then here's B, let's say X AY, BY, AX, BY, Y. So from this map here, we can just compose with this map we get a covariant action like this, right? This is a to the x is fixed up in the exponent there. And similarly here, a to the y is fixed up in the exponent, so we've certainly got a map like that. But from this map going from ax to ay, all we can do is precompose, and we get a map going this way with the by x fixed, and with the by, same thing. But remember, we're trying to get this, so we're stuck. Yeah? There's no obvious way of using the action on B and the action on A and putting them together to get an action on this exponent. So the result of this is that this does not work. Does not work. So the exponent, if it exists for two functors, is not going to be given pointwise. So now what do we do? Well, what to do? Well, you could guess, try to do some stuff, right? You could say, oh, well, if they're isomorphisms, then I could turn this one around somehow, and then they would be composable. Or you could take embedding retraction pairs, and then you could take on the one hand the embedding and the other hand the retraction, and so on. So there are lots of different techniques you could use. However, it's better to approach it in a principled way and try to see what it has to be, right? And then see if that works. That's kind of the machine of category theory gives you a way of testing what things ought to be and then deducing what they are going to be if they exist. So again, as in many cases, it's Yoneda to the rescue. Yoneda to the rescue. So let's do it like this. We want to have, we're looking for a functor b to the a, and we're trying to say, what the heck is it? Well, Yoneda tells us what it ought to be. If it exists, we know that it's got to be this. Right? Everybody remember the Yoneda lemma? Yoneda said that for any presheaf f, f of x is hom of the representable into f. That was the Yoneda lemma. Put it on a t-shirt. So let's use it. If this is going to be an exponential, then that's going to be isomorphic to hom yx cross a b. Right? If it exists, it's going to be that. So let's see if that works. Does this give us a contravariant functor of x? Contravariant variant in. So the proposal is we're going to take this as the definition right there. I mean, that's a set, right? This is a set of all natural transformations theta from yx cross a into b. That's our proposal for the value of this exponential functor at x. Yeah. Is it a contravariant functor of x? Well, let's see. We have, let's suppose that y goes to x. Well, we know the Yoneda embedding then is a functor, so that gives us this. Now we can cross that thing with a, because that's a functor, so that gives us this, yx cross a. And now we're homming out of this thing in this expression, right? So that gives us hom yx cross ab. This is a contravariant functor in the left-hand argument, so that gives us this, hom y cross a. So yes, good. It's a contravariant functor of x. If y goes to x, this thing goes to that thing. So we're done. And now you check, and now defining this to be the exponential, you go back through and check that this holds. I mean, this is the calculation which tells you that it's an exponential. So now what if you look at this thing and you say, oh, that's nasty, I don't like that. Tough luck. I mean, that's what it is. We just computed what it's got to be, and that's it. So the thing to do is just to get used to it, right? Start working with it, get a feeling for it, see what it means in some special cases and so on. But we know that if there is an exponential, this has got to be it.
Does it mean there is another way to express it
Absolutely, sure. I mean, this is an expression and it works. And now you can start calculating with that expression and find other ways to describe it that you like better and so on. But any other way that you come up with will be isomorphic to this one. So this at least proves that there is one, and this is a particular expression of it.
Is there another one you like better?
Depends on the special case. For the case where C is a poset, there's a very simple description of what this thing means, and it was one of your exercises. It was the last exercise. It's a kind of restriction operation. And yeah, I like that one a lot better. It's easier to work with. Okay, so that's our proof that variable sets is a Cartesian closed category. And in fact, there's a corollary now, because we know that, oh wait, there's one thing I didn't do. Oh, let's, first of all, we'll say the Yoneda embedding itself from C into sets to the C up. Now that we know that this thing is Cartesian closed, let's suppose that this one is also Cartesian closed. We can show now that that preserves Cartesian closed structure. In fact, any Cartesian closed structure that this thing has, even if it only has partial exponentials or only products for some objects, they get preserved going up to here. So let's check that. So products, if we want to make Yoneda of A cross B, what is that? That's Hom blank A cross B. Well, we already checked that you can pull a product out on the right of a Hom set, right? A cross Hom B. So that's Yoneda of A cross Yoneda of B. Because we know that these are taken pointwise, we just checked that the product of two functors is just the pointwise product of the values. So that's what we've got here. So that's good. And now what about exponentials? What is Yoneda of B to the A? Well, it's Hom B to the A. Let's give it an argument. So x. So we'll put the x in here. Right. I'll do it down here. X cross A, assuming that this really is an exponential in C. And now we use the Yoneda lemma again. The Yoneda lemma tells us that we can apply y right inside here and still get an isomorphism. YB. Because remember, this embedding establishes an isomorphism between these two Hom sets. So that's iso. And now by the first part that we just checked, this y distributes over x cross A. So that gives us Hom yx cross ya yb. But hey, look at that formula. That's this. That's this formula for the case that this thing is ya and this is yb. So that is exactly y to the b, y to the a applied to x. So there we go. Okay, so now the Yoneda embedding preserves Cartesian closed structure. It also gives us an isomorphism here between the Hom sets in here and the Hom sets in here. And now a consequence of that, remember we had our theorem on the completeness of the lambda calculus with respect to Cartesian closed categories, with respect to abstract models in Cartesian closed categories. Well, now we know that every Cartesian closed category embeds into one of this very special form, a Cartesian closed category of variable sets. Right? So this corollary says, in particular, given any Cartesian closed category, we can embed it as a Cartesian closed category into one of these special ones consisting just of variable sets. So in particular, if we're interested in completeness of the lambda calculus with respect to some particular class of models, we already proved it with respect to the very general class of all Cartesian closed categories. but each of those embeds into one of these very special ones of variable sets, and so we get a completeness theorem with respect to variable sets. So this completeness of the lambda calculus or simple type theory with respect to, well, variable sets. Variable sets. And the statement of the theorem is basically the one that I wrote down before, right? It says, given any, I'll just do it briefly here, given any terms in the lambda calculus, any lambda theory with basic types, basic terms, and equations, basic equations, any lambda theory, and any terms, let's say S and T, of any type X in that theory, if the theory proves S equals T modulo the basic equations of the theory, then for any interpretation of the lambda calculus into a Cartesian closed category of this special form, interpretation into any Cartesian closed category of variable sets, the interpretations of those two things will be the same. So this direction is, of course, soundness of the lambda calculus with respect to the semantics, and this direction is the completeness. If the terms come out to be the same under all interpretations in variable sets, then they must be provably equal via beta-eta conversion. Okay? And then there's a similar statement about inhabitation of types. So there's a term T of some type X if and only if in every model there's a term, there's a closed term T of type X, there's an arrow from the terminal object into the interpretation of X. So that's provability in terms of, so it's provability in terms of inhabitation, and it's provability in terms of the convertibility of the terms. It's completeness in terms of convertibility of the terms. And this follows now, so by variable sets I of course mean things of this special form. And that follows from this embedding theorem that we just proved. And in fact, there's an even stronger version here. I'll write it with capital letters. And the stronger version was actually proved only recently by me. And there's a paper by me and a student named Florian Rabe, which was in the recent, I think it's, I don't remember you'll see the reference if you just Google it. And this is a Kripke completeness. Kripke completeness. And this says same thing with respect to categories of the form sets to the P, where P is a poset. And that's a stronger, even stronger condition, or even smaller class of models, which agrees with conventional Kripke semantics, where you have, think of the poset as the poset of possible worlds in a Kripke frame. The ordering on the worlds is just the accessibility ordering, and then there's a very neat description of what it means to be a model of the lambda calculus in such a setting. That gives you a Kripke model of the lambda calculus. The types are just domains varying over the possible worlds. The products are pointwise. The exponentials are the thing that you asked about that I mentioned before. They're very nice restriction operations. And that's a complete semantics for the lambda calculus. Okay, so that completes the last lecture. Let's go on to the next lecture. Yeah, sure. It's a good time for question. Yeah.
Could you say a little bit more about this variable sets intuition?
Oh, sure. Yeah. Happy to. Let's look at an example that we had before was this sets through time. So there the poset was just omega, it's 0, less than 1, less than 2, and so on, forever and ever, right? And then an object in here, A, is just a set changing through time. So there, right, we have, it's a sequence of sets, and the elements change as you go from one to the next. You think of it as the set is developing through time. Some elements come in, some elements get identified, and so on. And then the arrows we saw were those ladders of functions, yeah? But equally well, you could have a different poset. So let's say we parameterize this where P is something like binary trees, something like that. Or P is a binary tree. So something developing like that. Well, then what is a functor on that going to be? Well, it's going to be a system of sets with some branching like this corresponding to this branching of the trees. So as the thing develops, the sets develop in different ways. It's not just omega sequentially, but whatever the poset gives you for an ordering type or for a branching type, the functors have to respect that branching type. So maybe you have the total binary tree, right? So at every moment there are two possibilities. Or maybe you have a poset. Another possibility is maybe your poset is the real numbers. And then you have continuous time, right? So you don't have this discrete nature, but for every two reals or for every two rationals, say, there's a way of connecting them. So there are lots of different examples like that that you can think of. Maybe the poset is, for example, all the open sets of a topological space. Right? And now you think of the space here, and then you think of the open sets and their inclusion ordering. And then the poset will assign to each open set for each region. Think of the space maybe as physical space, and think of the open sets as regions, right? And for each region of space, the functor will give you a value on that region. Maybe it's all the real valued functions defined on that region of space. And then as you go down, usually these ones are taken to be contravariant. So maybe as you go down from one region to the next, maybe the functor A takes this to all the functions, say, in the reals, and then defined on this region. And then as you go to a smaller region, you just restrict. So F goes to F restricted to the smaller region. That's actually the classical example of a presheaf. That's where the original definition comes from, is that idea of functions defined on regions of a topological space. But the idea is the same in all cases. It's a set which varies in a parameter. Right? In all cases, we have some poset. It has some elements, and they're ordered in some way. And then a functor on the poset is a family of sets, one for each element. And then every time you have an ordering like that, there's some way of changing from one set to the other. So that's the idea of variable sets. That's enough?
Yes, and it raises another question.
Okay.
So in both of the examples that you chose, the natural ordering on the exponent set was one way, and it looks like an op disappeared with respect to the generic discussion.
Yeah. It doesn't matter. I mean, it's perfect. It's purely a convention whether you order things one way or the other. Right? So I could have said order the numbers going the other way and then put op up here, something like that. This one became an op because it's a restriction operation. Right? So that's just conventional. I mean, every category has an op, and the op of a category will be op it to pick the category back out. So, is there another question? Okay, so what I'd like to do now is that's finished. Now I'll go on to another lecture, a whole new lecture. Okay, so now lecture 4, for which I have less time than I'd like, but it's worth at least getting started, is on adjoints, adjoint functors. And really, this is the most important of my 4 lectures, because adjointness if you take away anything from these 4 lectures, I would like you to take away the idea that adjointness is a fundamental, foundational concept of the greatest importance, which has been completely invisible and unrecognized until the advent of category theory. You need to have category theory in order to recognize the concept of adjointness and then develop its basic properties. So that's admittedly somewhat provocative. I mean, most people involved in foundations or logic would say something like, oh, maybe the notion of a type, or if you're a set theorist, the notion of element, or I don't know what, the notion of a function or something. But I'm going to say no, adjointness is maybe the unifying, I could be even more provocative, I could say it's the most important unifying concept in foundations of mathematics. Okay, so that's a big claim, so let's see how far we get with that. Let me just give you a couple of logical examples, which I hope to be able in the next few minutes to at least sketch. So one example of an adjunction is the adjunction between taking the product with something versus, this is how it's written, I'll explain it in a minute, versus taking the exponent by something. So this captures the basic operations of the lambda calculus. Another example of adjointness is the product operation itself. We'll see in a minute that that's adjoint to a certain trivial operation that you may not have even recognized, but it's there. And moreover, that's adjoint on the other side to the coproduct operation. So these things are related to each other in that way. Also, the notions of induction, recursion, and then things defined in terms of them, like the natural numbers and types of lists, all kinds of inductively defined types. These are all examples of adjoints. And similarly in logic, of course, things related to this, like conjunction, disjunction, true and false, exponentiation. These are adjoints. Also, the quantifiers. I think it's quite remarkable and beautiful that the quantifiers are examples of adjoints. And even in dependent type theory, the type theoretic operations on dependent types, sigma and pi, are also examples of adjoint functors. So if I can show you that all those things are adjoints, then maybe you'll believe me, or at least you'll understand my rhetorical flourish of claiming that adjoints are a concept of fundamental logical and mathematical importance. Actually, these are just a few examples that occur in logic. But actually, adjointness occurs all over mathematics, from the highest level, from the lowest foundations to the highest abstract constructions in mathematics. There are examples of adjoint functors. So let's start with that first example of product and exponential in order to get the general notion of an adjunction. So here's our example. So we saw that when we have products and exponentials in a Cartesian closed category, there's a bijection between things of this kind, that is, arrows out of a product, and things of this kind, So here, fix A in some Cartesian closed category C. There's a bijection between things of that kind and things of this kind. Right? And that's the fundamental operation of currying or evaluation, which mediates that bijection. Given something like this, you get one like this. Given something like this, you get one like that. And moreover, if you compose those operations, you get the identity back out. Okay, so what we have here is, on the left, we have a functor, And we've checked that that's a functor, right? F of x, namely it's x crossed with a. We know that that's a functor. On the right, we also know that this is a functor. Call it g of y, and it's y to the power of a. And we have an isomorphism between maps out of F and maps into G. And moreover, we know that this isomorphism, so we have an isomorphism between, but moreover, the isomorphism, as we said before, doesn't really depend on x and y specifically, right? It's parametric in x and y, or it's polymorphic in x and y. It's an isomorphism between these two structures of product with A and exponent by A. And we learned last time how to say that. It's natural in x and y. It's an isomorphism, and it's natural in both arguments, x and y. Well, that's the definition of an adjunction, exactly there. So the definition is this. An adjunction between two categories, say, between categories C and D, consists of, so here's C, here's D, a pair of functors, F and G, going back and forth. In this case, the functors were on the same category C, but that's not essential. We can have an adjunction between two different categories, such that there's a, well, such that, wait a sec, don't write things down until I've finished because I might change it. I'm making this up as I go along, you know. Such that for all x in C, y in D, there's a bijection, well, of exactly this form. F of x into y corresponds bijectively to x into g of y. And moreover, it's a bijection, it's natural in x and y. Good. So that's the definition of an adjunction. Just by way of terminology, is this pen running out now? Or terminology. So in this case, I'm going to say F, and I'm going to write a backwards turnstile G, just because that's the convention. And we call this one the left adjoint for obvious reasons, left adjoint. And this one is called the right adjoint. And so we already had one example. That is, we showed, well, number one over there, right? We showed that the operation, the functor cross with A, is left adjoint to the functor taken exponent by A. So that's our first example. Right? Everybody good? That's exactly this example. Let's do another one. Remember, in the case of products, we said x into A and x into B gives us a map x into A cross B. Going back and forth, right? We said that's the universal mapping property that characterizes products, that defines products. But let's look at what's going on up here. What is that? X into A together with X into B. Really, we can put that together as a single map of the form X, comma, X goes into A, comma, B. That's a map in the category C cross C. So what's above the line here is exactly a map in C cross C, whatever our category C is, right? And this is an object of a special kind. Let me call it delta of X. So down below here is C. So what is delta of x? What do I mean by that? Well, let's do it this way. I have a functor. Here, I'll just write it right here. C cross C. I have a functor delta going up into C cross C. It takes an object x and it just pairs it with itself. It's a very trivial kind of operation there, right? Remember, the objects in here are pairs of objects. Right? Here I take a single object, I bring it up here, and I take just the object paired with itself. And that's exactly what's going on here on the left, is such a delta. And now I'm saying, map that into anything. That's what's happening on the top of the line. That will correspond exactly here to the product of A and B. So on the top of the line, I have something like this. And on the bottom of the line, I have x mapping into A cross B. So that's exactly saying that this operation delta is left adjoint to the product operation. Good? Everybody see it? Yep.
Could you unpack what it means to put that bijectionally in the definition of the definition to be backward x and y?
Let's do it later together, okay? If you work it out, you'll get it. It's just time consuming, and I don't have the time to do it, okay?
What is the functor g here?
Here,
Yeah.
the product functor. It takes two objects, A and B, and it takes them to their product. Is it good? The left adjoint is delta. The right adjoint is the product. You know what? There's another adjoint over here, a left adjoint to delta. Should we see what it is? How would it look? It would go like this. Anybody guess? Oh, I'm sorry, I already gave it away.